John told about the excellent tool of INSAR, but in urban areas especially, it doesn't tell anything about what is driving the process. As both Luke and Guadalupe was saying, it is different causes for these ground movements. And yes, there you go. The urban areas or the cities are very complex. I'm going to show some cases from Norway. This is Oslo, our capital. In the waterfront, it's been development, a huge development since the early 2000s. And all new constructions in Norway are foundly piled down to bedrock, and it's very stable. Let me see if I can move this. And this area is a very known financial area, which was built in the 2014 and finalized in 2014. The road in front of it is piled down on over 200 construction or metal pilings down to bedrock. So everything that's newly built is safe and sound. The problem is that Oslo is an old city, and people have lived there before. So the old ground or the old buildings are not built in a safe manner. So this means that the newly constructed buildings are stable, while the alteration in the ground changes the ground condition and makes the oldest part of the town move. So the color schemes have been showed. Blue and green is stable or actually uplift, while yellow to red is sinking. So this is the train station where the train racks, so train trails out of the city. And the newly construction is the front on the waterfront side of the train station. In addition, there's built a pedestrian bridge across the tracks, as you see in the background there. This bridge showed it's stable on one side with the new piled on the newly construction area, while on the other side it is on the older part of town. So within 3 years, this bridge has moved 17 centimeters. So the damage of the construction is quite visible. As John told, we can decompose the data sets. We can see how much the substance is, and also which direction it is moving. So the movement in the ground causes damage to buildings, and this building is actually being demolished because of its damages. And also, as Guadalupe showed, the buildings are really getting a rough time. So is the construction of the pipelines in the subsurface. Damage, non-visible damage, is also being kind of mapped in pipelines and subsurface constructions. So I'm going to go back to another place. It's Fredrikstad. They're planning a new road or train connection in the area, and they need a new station in this Grønli area. It's the same area as really showing on the INSAR data of being not stable. And we were looking back and trying to figure out what is causing this instability. And this old bridge is constructed in 1975, and the area has shown movement or subsidence since the early 75, or possibly even more. We're just lacking data. And the subsidence is, of course, damaging constructions. This bridge, constructed in 1987, is severely damaged and quite visible of the causes. So even if the topography in the area is quite flat, it doesn't mean it doesn't have topography, because the bedrock is sticking up in the pinkish area color here, while the blue is the sensitive clays from the glacier or glacial area. And also beneath the drift deposits, there are mapped areas or zones of deep weathering and quite fractured fault zones. So here we map the topography of the bedrock, and you see that, you know, the visual topography is quite flat, but when you see the topography of the bedrock, it is quite rough. Yeah, and we also think that in the so-called valleys, the fracture zones are beneath. So when you alter the groundwater and the pore pressure in the sensitive clays start to alter, and combined this over a very long time, this causes subsidence or compaction. And the difficulty of indicating when or why the subsidence occur is that this is a complex graph, but it takes time, and it's difficult to actually say how much time is going to, from incidence or alternation in groundwater, is going to be shown on the surface and causing damage to the buildings. So the time question is hard to answer. So we went back to earlier satellites and tried to show with the satellite data the movement of the area. And it's been continuously, at least from 1992. And it was combined with the Sentinel-1, which is the newer satellites. And the clear difference is that the Sentinel-1 satellite has a much more frequent data collection than the ERS satellite. But the trend of the movement is the same. And when you combine the two, you see that, you know, it's been a quite large subsidence since 1978, and it has been more stable, but the stability of the subsidence is now at 4 millimeters a year, which will add up in quite some centimeters over time. So moving to Bergen, which has a completely different setting. This is the Bryggen, which is a UNESCO preservation area. It's old buildings that have been quite damaged because of groundwater reduction. New buildings around it has been constructed, and that has caused leakage in the groundwater. While the old buildings are on cultural layers, that means actually human waste that is close to 100% organic material, and they are very sensitive to changes in groundwater. So since 2010, it was a Save the Bryggen project, which a lot of remediation has been put in to save the buildings and stop the subsidence. And as you see, these shops had to change the windows quite frequently because the buildings were moving so much. So urban groundwater cycle is very complex, and you need a variety of knowledge to cope with it. And here's a schematic scheme of the Bryggen area, where you have the bedrock, you have the drift deposit, and then you have the cultural layers. And they are up to 10 meters deep and extremely sensitive to exposure of air, where you decompose the organic layers. And showing how much subsidence, we compiled the data from 2012 to 2016 just to show. I will try to, yeah. And you see especially the Bryggen area is subsiding quite a lot. And I'm showing this again just to prove the point that the area is very prone to subsidence and damage. So over 4 years, you can see the development. To check if the sensor data was actually giving the, you know, validating the data, we combined it with ground proving measurements of subsidence, and the Massachusetts student did this work. So the field measurements are showing the same subsidence as the INSAR data. So to improve the groundwater level, sustainable urban drainage systems were applied. They were built in the backyard of the Bryggen to infiltrate as much water as possible. And they look quite nice. And if you want to have more information about SUDS and the Bryggen project, this is the way to go, climatescan.org. And the groundwater was measured quite rapid. It's an automatic logging showing that the groundwater was, with the remediation and the stop of the leakage, the groundwater was increasing again back to the level which was satisfactory. And then also, as you see of the data today, the Bryggen area is quite stable. So what we see is that, okay, it's been subsiding quite a lot, and this is only data until 2019, but it's at least leveling out. Let me just skip it. So there's some publications on the problems. So just to finish up, John touched into the Trondheim. Everything from the river and out, everything above the line is man-made ground. And as you see, the pier area or the for waterfront here is also subsiding quite a lot. So it's man-made ground. It's construction that is not most likely not funded on the bedrock because it's quite deep. And in addition to subsiding in the buildings, we have the problem of increasing sea level with the climate change. And also being at the waterfront, it is prone to possible subsea landslides, which has occurred previously. So that was all for me. Thank you.